Alright, it's been almost a week since I recorded a video. Time just went by. Anyway, I'm continuing work on my motor controller and putting together the different drivers. I've gotten a lot of things working since the last video. I have things connected like this. So I have a servo. I have actually two servos. These are DC servos, so they're not actually using all of the functionality of this motor driver. This is a three-phase motor driver. It's designed to be a three-phase motor driver, but driving DC servos is a very simple application that is easily achievable with a circuit like this. And right now I'm looking at the I2C driver, which there seems to be a problem upon reset. So what is happening is that sometimes, or actually quite often, the I2C code just is not able to access the MCP4461 chip, and this chip is a digital potentiometer, which I use to regulate the overcurrent set point on the MOSFET driver, and I'm guessing that there could be something related to how it is reset, and maybe it is not really behaving properly on the I2C bus. But the end result is that if the power is powered off and the board is powered on again, then it is impossible to communicate with this chip right now. If the STM32 is reset manually and the power remains on, then everything works fine. So it is that leads me to think that it's something related to reset. So I'm going to experiment a little bit with the reset, and I'm going to see if I can if I still get the issue when removing the power. And the thing is that sometimes when just powering off the supply, you actually have to wait for a while before the issue appears, because there could be a little bit of voltage left in the power supply capacitors, which takes a while to discharge. So I'm going to be powering off my supply and waiting maybe 10 seconds or a little bit more than that, and then powering it on again and checking if the issue is still there. But what I want to do first is just add the support for reset pin and write protect pin, and I'm actually going to be toggling the reset pin and waiting for about 1 millisecond before continuing with initialization, just to make sure that that it's not the reset, just to make sure that it's that the chip is actually being reset properly. So let's see, we have the write protect pin, and I'm going to just save the write protect pin. So I'm reading all of this from the device tree. I'm also supplying the GPIO, and in this case the GPIO is actually an SPI GPIO. So the way I've designed this is that I have an SPI GPIO that controls these control lines, because I didn't have enough pins on the microcontroller to be able to control the reset and the write protect here. So it could be something also maybe related to how this GPIO is set up. But what remains is just to figure out what exactly is going wrong. Let's see. So I have the device tree node defined here. This is the device tree node for my for this particular instance of this chip, and I supply the GPIO, which is MCP4461 number 1. I have 2 chips, and the reset pin is pin number 5, and the write protect pin is pin number 6. Oops. Okay, let's see here. This is going to be moved here. And this is where we're going to reset this. So we're going to do a GPIO. Even though I'm supplying GPIO default value of 1, I'm gonna do it like this anyway because it's easy enough to mess up the definition of device tree. So we're gonna set this first, and then we're gonna reset it to generate the reset pulse, and then we're gonna set it again. Let's see, GPIO self reset pin, and we're also gonna set first GPIO set, and write protect is also active low, I think. Pretty sure it's active low, yeah. So we're gonna set GPIO. We don't want to write protected just yet, just to rule out any possible issue with that. And I'm gonna sleep for a while, and GPIO, let's see, reset. So if this doesn't fix the problem, then it's probably something else. But it's definitely related to this chip, because the communication with this chip actually fails. Let's see. Or actually, I take that back. It could be like if this fails now, it could actually be something related to how the I2C device or the I2C peripheral on STM32 is being reset. I'm reinitializing the device, I'm resetting it through the RCC, but it still could be something, because this is the first device here. So if this doesn't work now, I could actually maybe move something else to be the first device here, and I can check if the problem still persists. And if it does, then it's related to the actual I2C peripheral on the STM32 chip. Let's see. But doing this reset is still a good idea, because just to make sure that the chip is completely reset before we actually start initializing it. Right, there is something else I want to do here. I want to add because this is going to be an analog device, I want to add analog device functions to it, because it will expose the analog device interface to the rest of the system. So we can do it like this: analog device register self dev. And we have the analog ops, which we need to define. We're going to do it like this: static struct analog device ops analog ops equals write analog write and read analog read. So this is kind of like the equivalent of virtual functions, and then we're going to implement them static and analog. Let's see, MCP4461. I usually prefix my functions because I like that. When I then do like a dump of all the symbols, I can see that this function belongs to this driver. So MCP4461 analog write. And this will take analog device tdev, which is a pointer to the ops structure inside this. So this is going to be a pointer to dev ops, and this allows us to get the pointer to the actual driver structure very easily. So like this. Let's see, int 32. I think I'm going to check that. Let's see, so this will be channel and float value, and then I can get the pointer to the actual driver instance by doing like this: struct MCP4461 self is container of dev, and then MCP4461 dev ops. So what this does is basically tells, this is a macro that calculates the offset from like knowing the dev, knowing that this is a pointer to the member of this structure, which is located under analog device ops. Let's see. Okay, I couldn't go to that one. Sometimes it doesn't work. But anyway, this one has a... actually, I know why it doesn't work, because this one is defined by a macro. So that's why it didn't work. So it's impossible to do any kind of completion with that, because it's actually defined by a few macros that I wrote for defining device subsystems. So this one is actually defined here. Let's see. I can go to lib firmware include and driver there. So this will be a structure that's defined like this. It's going to have a list. So this is going to be a device class. All device classes are placed into list, and it will have a structure that's called like device ops, which is prefixed with a class, and this is the structure that we define then for the analog device in the analog H here. So the pointer that is supplied as dev is actually going to be this, going to be pointing to this pointer here. And let me just go back here to DTS like that. And then I will write the value to the wiper register. Let's see, let's do this on sign int, and the writing is done like this. I'm gonna move this test code, and I'm gonna just do it like this. So, and the register is actually 9 bits wide, so it's the most significant bit is actually going into the byte that represents the register address, which is a bit weird. Like, it's just messy, but that's how they did it. I'm gonna go to this data sheet for this chip. Where is the data sheet? Actually, I think that was the right data sheet. Or maybe that was the one for the LEDs, actually. So, where's the register list? By the way, here's the reset waveform. This is how they want this chip to be reset. And even though this is like 50 nanoseconds, which is very small, I'm still gonna just wait for a millisecond just to be sure. And once I figure out what the problem is, I can remove those little lines where the code sleeps. So let's see. I want to find the register map though, so I can check all of the addresses. Where's the register map? Device commands. Yeah, so there is actually 2 bits. which represent the most significant bits of the data. And I just want to see here. So this chip, by the way, supports both volatile and non-volatile. So it has a set of registers where it has the volatile registers are for the current setting, so you can actually just change the setting in RAM. And if you write to the non-volatile wiper register, then you're writing to the internal EEPROM on this chip, which will be the value that it will load when it restarts. So it can be good to program permanent values once into the wiper register. That would be the default next time the board is reset. But for now, I'm going to be writing just to the volatile registers, and it's 10 bits of data, which means that I need to separate this into the register address and the data. The data byte is going to contain just the low 8 bits. So first of all, I'm going to convert this float value. So analog write accepts. I kind of haven't decided what if I want to have a standard set of like 0 to 1 or maybe a voltage. But I think for the most part I use 0 to 1. So any analog outputs are expressed in a float value that is between 0 and 1. So that means that I could just do like this. I'm going to make this a uint16. And I'm going to make this data. No, actually, because data is going to have to be uint8. Make this val, and then I'm going to make this 3ff times value. I place a lot of casting in the code. For one thing, I have warnings enabled that disallow direct cast to a float, or if I have anything that looks like an int, or if I cast a float to an int, that will create an error from the compiler. So I have to do that explicitly, and I like to just have explicit casts so that there is no ambiguity of what is being converted to what. So this will be a floating point value that represents all of the 10 bits set, and then it will be multiplied by value. And actually, we can do like this: value equals, just to avoid any kind of errors in the value. And then when I multiply this by value, I get something that is between 0 and 10 bits. And then I have this uint8 data equals val, the last 8 bits. Return 0 on success, which should probably be like int ret equals 0. this will be also ORed with val 8, rotated by 8 bits. So this will be the two most significant bits of val. And of course, this is total bullshit, because that was just the test code. And what I need to do here is just pick the reg address. This will be reg, and this will depend on the channel. Let's see here. So make this 0 and do a switch statement, because we really want to make sure that if the channel is out of range, then we should just be returning an error, not trying to write to some register that is not the correct register. And yes, I could have come up with some smart algorithm for figuring out the register address, but I think this is more clear. I think this is just as clear as it gets. We have wiper 0, 1, 2, 3, and depending on the channel, we write to the wiper 0, 1, 2, 3 register, the volatile one. And I could actually also provide like this, so I can have a few more channels that write into the non-volatile registers. And I make it very clear which one is which here, so this will be NV, wiper 0, 1, 2, and, oh yeah, of course, 3, NV, like that. And default is return E in val. And we can actually do a print K here. This would be MCP4461. Or should I do a print K? Actually, if this error ever occurs, it's going to be flooding the console with messages, so I don't want to do that right now. Let's see. And then I could just do like this. So I2C write buff is going to return the number of bytes written, and we're not interested in returning anything besides 0 on success. So I will check if this is less than 0. Yeah, and I should be doing it like that. And if that is less than 0, then we return red, otherwise we return 0. This will be self-adder and self-I2C. And reg write value data. And data is a pointer. And I've also written some helper functions which allow just writing data like this. In fact, why not? Since we have the helper functions, this is not actually needed. Okay. Analog read, probably not necessary for now. But all of the methods still need to be defined. There shouldn't be any zero pointers anywhere. So we just define it and return -1. This will be read, of course. I'm going to disable the automatic search. I don't like it. This function is so annoying. And because I've now removed this little test code that I had, I also need to add. I need to also write the default value for the overcurrent protection to make sure that it's sufficiently high so that I don't get overcurrent fault when I just start the MOSFET driver. So the way I'm going to do this is add a link to this chip here. Let's make this. Let's see. This could be. So I'm using this also for the LCD contrast signal. So what should I call this chip? I could call it MCP4461. Yeah. I have to add a label here because this label is the only way to reference this node from another node. And I need to reference this node from my application. So I also have my application implemented as a driver. And it gets configured through the device tree like this. So we will have OC pot equals MCP4461 and I can then get this the pointer to the analog interface in my application, and it will point to this particular device on the board. So my application doesn't actually need to know anything about the actual board it's running on, and instead it can just do like this. This is really messy code for now. I'm going to be doing complete code review once I'm done with a basic demo. But for now, I'm just concerned about getting things working. Let's see, analog device OC pot, and then I can get this OC pot here. And we should just configure it here as well. So it'll be channel 0 and 1, I think, or no, it's channel 2 and 3, of course. So channel 2. Yeah. Should I use a define? Yeah, I probably should. Like OC edge motor 1. And this will be 1.0, set it to maximum value. So I find it very useful to use a float between 0 and 1, because then I don't need to worry about how many bits the actual chip supports. So it can be a 10-bit potentiometer or an 8-bit potentiometer, and I won't need to change my code in the application. And I'm going to add this here as well. So this will be analog device. Let's see, pot, and this will be analog find by rev. And these functions are also defined by my macro. So they're generated, they're templated in C using macros. They basically provide simple ways of retrieving pointers to the actual device interfaces based on references from device tree. So this OC pot is actually this field here in the device tree. And this will be OC pot. I should be doing the same thing here, but yeah, this is going to be reviewed. This is a basic draft. So this should work, besides the fact that I also need to define the macro, not macros, but the definitions for these channels. OC-pot, OC-arch. Damn, this is, I'm not happy with this. I'm not happy with this. But I'll have to do it this way anyway. Motor 1 is channel 2, and motor 2 is channel 3. This will probably not build, but it's a good step forward, and it's time to define all of the things that are missing here. So, include the analog interface and vreg. Okay, right. So I misplaced the NV. It should be here. Just going to explicitly cast this. And this is also, because reg is an int, it shouldn't be an int, it should be int 8. So I'm just gonna check if reset pin. Let's see. If we supply, if the user supplies GPIO in the device tree, then both reset pin and WP pin have to be specified as well. And I return the invalid error. And this will be UN32 as well, so that I don't need to cast and call to this GPIO set. Just cast them here. Actually, because that is an int, it kind of makes sense to check if it's just less than 0. Catch all of the negative values. And I'm going to print out the ready as the last thing I do here. So maybe this works better. Yeah, so it flashed. And you can see the board is actually powered now. Let's see, where's my camera here? So the board is powered. There is something weird going on. The LEDs are not actually moving. Like they're not dimming, they're not changing their brightness. They should be changing the brightness if the board is running. If the board is not running, something bad happened. Something really bad happened. Let's see. What could have happened? I'm going to attach to this board using STUtil. Let's see. And specifying the N flag makes sure that STUtil doesn't restart the chip, so it just attaches to the chip. And then I'm gonna go to, let's actually do like this. So I used to run the debugger from the directly from NVIM, but I realized it's probably better to just run it separately, because the plugin is a bit buggy. And we are stuck in the I2C SR1. So my I2C driver right now is a really bad driver. It uses while loops. I usually say that you should never, ever, 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 ever use while loops that block the code. But that's what I'm doing right now. But that would be subject to complete review and refactoring. And I'm gonna get this driver to work using interrupts. I have several drivers for other chips that use interrupts, but not on 429 yet. But that's hopefully a very quick thing to fix. But the advantage of using a simple driver is that it's easier to find other faults that may be there. Like, for example, it's easy to just get the program to hang somewhere here instead of this being like timing out and then continuing, and the error kind of always being there. So since it's just hanging there in this, just waiting for this flag, I can just check where it is, and it's in the analog write, and trying to write the register. So obviously there is still something going on here, and I'm gonna check the console here. Let's see. So it seems that it did start. So it did start 2 chips here, but then it failed upon the application actually trying to write. But I think I know why it failed, because it's quite obvious why it failed actually. It could be that I still haven't added any locking to this, or it could be something else. Like for the most part right now, the way the application is written right now, even though there is no locking in places where there should be locking, it should still work, because it's using only one control thread, and the only other thread that can access things concurrently is the console thread. So as long as I don't do anything from the console, I'm not going to get any weird faults happening, or I shouldn't get any weird faults happening. So I'm going to check if the write protect pin is on the, let's see, I'm going to check if the write protect pin is high, to make sure that the chip is not write protected. Because if the chip is write protected, it's probably not going to acknowledge any writes, and that could be what is happening here. Let's see where it's hanging. It's hanging on. Let's see. Check event. Yeah. So the chip is not acknowledging any data that's being written to it, which could be explained by the fact that maybe the write protect is set to low. Okay, this seems to be working. And I need to check which one is write protect. Okay. Checking the write protect, and the write protect is high. So I'm not even connecting any ground, I'm just checking the value. So the signal is very noisy because I don't have the ground connected anywhere, but it still works because like everything is still connected to kind of the same ground, but it gets very noisy. So write protect is enabled, or rather it's high, so it should be disabled. The chip shouldn't be protected, but I'm gonna double check if that's really the case. Maybe there is a timeout after writing. Or maybe there is something wrong here actually, because is this really... So it seems to be that this is 9 bits and not 10 bits. But the chip won't care anyway because there is an X there. Okay, so write protect is only for the non-volatile memory. That's good to know. It means that it doesn't matter for the volatile registers. But why is it not responding? I'll check here. So this is happening here. And reg ends up being 99. So reg 99. Interesting. So why am I getting 99 there? So the command byte according to this should be 0, 0B, and reg. Oh, so wait a minute here. Let's see here. The reg shouldn't be 99. At least the high bits of reg shouldn't be 9. Oh, I see. Could it be that I'm actually writing to the non-volatile register? Maybe I was writing to the non-volatile register and not waiting enough time before writing to the next register. Let's see. This will just make sure that there is no bits set in the high byte of this value. Otherwise, it will mess up the register that I'm writing to. And reg should be. It should actually be 2 and 3. So something is wrong with this calculation. And upright is 0. This is still stuck in the same place. Oh, of course. It's 63 actually. So I was looking at 99, and I kind of assumed that that was in hex, but it was actually a decimal number. So 63, that looks better. 63 should be writing 2. Yeah, this should be 0, and this would be 6. That's volatile wiper 2. So what about the reset pin? Maybe I forgot something here. Let me check the reset pin. The reset pin is high. So why is the chip not acknowledging any bytes being written? So actually, so reading the status does work, because I can see that it's been started here. So it has read the status and it went past to the ready line. So MCP4461 ready, 2D and 2C. Maybe I forgot to set something here. Let's see. Maybe it could be something as simple as us not saving the address. Look at this. Address. Of course. That is just so stupid. That is just so stupid of me. I forgot to save the address. So of course it was not working. Because I was trying to access address 0. I don't have anything on address 0. Okay, so now it works. It was as simple as that. Sometimes the solutions to problems are very simple, and sometimes they're due to stupidity of the person that is designing them. Okay, so now this is working. This is pretty good. So you can see the LEDs are dimming. This is the default behavior I've programmed for the LEDs for now, and there will be other functions bound to the LEDs and buttons. But for now, this is working. So next step now is to actually power off the board, and then try to power it on again and see if it actually powers on. So I'm going to wait for a while, and after it has discharged completely, I'm going to power it on again. And powering it on again, and it probably wouldn't power on. It did! Okay, I'm going to try this again. Could this have fixed the problem that I had with I2C? Just resetting the chip manually before initializing it. Powering on, and it's working! God damn it, no more problem to fix. Okay. Alright, that's it for this video. Fixing MCP4461. Not responding to commands after powering on the board. So the fix for the issue has been to manually toggle the reset pin, and that seems to have solved the issue. Thanks for watching.